So let's look how we can find the probability of an earlier event given the probability of a later event. So we'll get to the formula soon, but let's talk a little more about the problem above. Suppose we want the probability of an earlier event given the probability of a later event. So let's say we want the probability that the ball came from box 1 given that it's red. So let me remind you of the diagram. Okay, so here's the diagram, and we want the probability that it came from box 1 given that the ball that was drawn was a red ball. So it could have come from either one of these, but we need to find the probability it came from box 1. Okay, so if you'll remember this formula up here, I'm going to apply it to the B1 given R here. The probability of B1 given R is the same as the probability of B1 intersect R divided by the probability of R. Now also recall that if I wanted the probability of B1 intersect R, I could write two ways. I could either write it as the probability of R times the probability of B1 given R, or I could write this as the probability of B1 times the probability of R given B1. The problem is, in the first formula, is the probability of B1 given R is in this calculation, and that's actually what I'm looking for. So that doesn't really help me much. But in the second calculation, I can work with this second calculation. So we do know that the probability of R given B1 is 7/10. So we know this, and so remember, this is the probability of R given B1, and by the way, this is the probability of B1. So we know that the probability of B1 intersect R is equal to the probability of B1 times the probability of R given B1. So now let's go back to the above formula that I had up here, and let's see, where was it? Hang on just a second. Okay, here it is. So go back to this formula up here, and now let's replace this B1 intersect R probability with what we got here. So instead of this being the probability of B1 intersect R over the probability of R, we can say it's the probability of B1 times the probability of R given B1 over the probability of R. And now we know the probability of B1 is 1/6. We know the probability of red given B1 is 7/10. And remember, a while ago I showed you how to find the probability of R. All you had to do was multiply all paths to R together and add them up. So one path to R was the 1/6 times the 7/10. The other path to R was the 5/6 times the 3/5. So the bottom, we're just summing the products of the paths to R. So like the 1/6 times the 7/10 and the 5/6 times the 3/5. Okay, now I know that seems very complicated, but let me just show you all I really did here. All I really did, if you think about this, to find the probability of B1 given R, now you're going to love this. So all I did to find the probability of B1 given R, go back to the diagram and I'll show you. In the numerator, I just multiplied the two branches that go from B1 to R, and in the denominator, I multiplied all pairs that go to R, 1/6 times 7/10 and 5/6 times 3/5, and added them together. So in the numerator, I just multiply these two branches, B1 to R, and in the denominator, I sum the product of all branches that lead to R, which was B1 times R over B2 times R, or plus B2 times R. Okay? So there's actually a literal formula that works better. And so let me give you the literal formula. the literal formula for the probability of this earlier event B1 given R is the product of the path from B1 to R divided by the sum of all products that lead to R. So again, the numerator is the products of the path to R. The numerator is the product, actually that should say is the product of the path B1 to R. So that would be the 1/6 times the 7/10. So I need to correct that. And then the denominator is the sum of all products leading to R, which would be the 1/6 times the 7/10 plus the 5/6 times the 3/5. And so the probability of B1 given R is just 1/6 times 7/10 over 1/6 times 7/10 plus 5/6 times 3/5, which is 0.189. Now let's try it for the probability of B2 given R. So using the same premise, the numerator would just be the product of the path from B2 to R, 5/6 times 3/5, so you see that's the numerator, and the denominator would be the sum of all products that lead to R. So 1/6 times 7/10 plus 5/6 times 3/5. Let's see, it should be 3/5, not 2/5. Okay, because it's to R, not to W. All right. So anyway, I'll correct that in the notes, but that should be a 3. I'm not sure if it's going to give us the right answer, but I know that should be a 3. It's right. I just did a typo right there and had a 2 instead of a 3. So again, the probability of B2 given R, the numerator is the path from B2 to R, 5/6 times 3/5, and then the denominator is the sum of all products that lead to R, 1/6 times 7/10, 5/6 times 3/5. And that would give me 0.811. And notice that if you add these two together, that it adds to 1, because if you do get a red ball, it either had to come from box 1 or it had to come from box 2, because there's no other place it could have come from. So again, I like to stick with the literal version of Bayes' formula, and you can disregard the mathematical formula, the form, and just use the literal form. So the probability of A given B is the product of all branch probabilities leading to B through A, or if you prefer, you can just say from A to B. And then the sum of all branch products leading to B would be on the bottom. Now, I'm going to talk just real briefly about independence, but don't worry too much about this. If you take an advanced course in probability, you can study this more. Independence simply means that the events do not affect one another, like the probability of rain today and the probability of drawing an ace from a deck of cards. I doubt whether it rains today is going to affect what cards you draw from a deck of cards. So events A and B are said to be independent events if and only if the probability of A intersect B is equal to the probability of A times the probability of B. So let me just give you a simple example. Suppose the probability of A is 0.5, the probability of B is 0.3, the probability of C is 0.2, and the probability A intersect B is 0.15, and the probability A intersect C is 0.2. Well, if you multiply the probability A times the probability B, you get 0.15, and that's equal to the probability of A intersect B, which is 0.15. So that would tell me that these are independent events. But if you multiply the probability A times the probability of C, you get 0.1, and the probability A intersects C is not equal to 0.1. So in this case, A and C would be dependent events. So for an example, suppose the probability of A is 1/4 and the probability of B is 2/3. What would the probability of A intersect B need to be for A and B to be independent events? And the answer is simply the product, 1/4 times 2/3, which is 1/6. Now on the next video, I'm going to just do some examples of Bayes' formula for you.